So today, we're diving into one of the biggest puzzles in all of medicine. How do we find new drugs? You know, it used to be like searching for a single magic needle in a haystack the size of a galaxy. But now, well, now we have these incredibly powerful computers acting like the ultimate detectives in the hunt for life-saving cures. Let's get into how they actually do it.
So what's the actual challenge here? Well, to fight a disease, you need to find one single, perfect chemical compound, the one perfect key that can fit into a biological lock and just stop that disease in its tracks. Sounds like finding a needle in a haystack, right? Oh, but that haystack is so much bigger than you can possibly imagine. Just how big are we talking? Well, one of the biggest chemical libraries that researchers use, it's called zinc. It contains around 35 million different compounds. 35 million! Think about that for a second. Physically testing every single one of those in a lab, it's just not possible. It would take decades and cost an absolute fortune. So, where do you even start?
And this gets us to what I call the billion key problem. See, for a drug to work, it has to fit just perfectly into a specific biological target in our bodies, like an enzyme or a protein receptor. The best analogy, and we're going to stick with this one, is a lock and a key. The disease is the lock, and the drug is that one unique key that can pop it open and fix the problem.
The old school way of doing this is something called high-throughput screening, and it's basically a brute force attack. You've got scientists in a lab physically testing thousands upon thousands of these chemical keys in test tubes against the biological lock. It is unbelievably slow, it is ridiculously expensive, and it's really just a massive game of guess and check.
But what if you didn't have to try every single key? What if you could hire a kind of digital detective who could analyze the lock, then search a gigantic virtual warehouse of keys and just hand you the ones that are most likely to fit? Well, that's exactly what modern science is doing right now.
This digital detective work has a name. It's called virtual screening. You might also hear people call it in silico screening, and that's actually a pretty cool term. You know how in vitro means in glass, like a test tube? Well, in silico literally means in silicon, as in on a computer chip. So instead of using test tubes, scientists are using powerful software to sift through millions of compounds, kind of like a digital molecular sieve, just to find the absolute best candidates for testing in the real world.
Okay, so our digital detective is on the case, but it doesn't just have one way of working. It's got two really distinct strategies for hunting down that perfect drug, and the method it picks really depends on the clues you have at the very beginning of the investigation. And these two approaches are actually beautifully simple to get your head around. On one hand, you have receptor-based screening. Think of this as the know the lock method. This is what you use when you have a super detailed 3D model of the biological target you're trying to hit. On the other hand, you've got ligand-based screening. This is the know the key method. You use this when you don't have a good model of the lock, but you do have a few keys that you already know work.
So let's break down that know the lock method first. Step 1. Scientists build a really precise 3D model of the target protein. Then, this special software, it's called a docking program, digitally smashes millions of different compound shapes against it to see how they fit. It then scores every single fit based on physics and chemistry. The compounds with the highest scores, those become your prime suspects, your hits. And here's the real magic of this approach. Because the computer only cares about what fits the lock, it can find totally new, completely novel types of drugs, keys that nobody has ever even thought of before.
All right, now for the know the key method. In this scenario, our detective already has a few keys that are known to work. The computer's job is to analyze those keys and figure out what they all have in common. You know, maybe a specific shape or a particular electrical charge. It uses those common features to build a kind of digital most wanted profile for the perfect drug. Then it just scans the entire library for lookalikes that match that profile. This is an awesome method for finding better versions of drugs we already have, but here's the catch. It's pretty unlikely to find a completely new class of drug.
So we have these two really powerful digital strategies. But what does this all mean for actually making new medicines? I mean, why does this matter so much? Well, the impact is absolutely enormous.
Honestly, the impact is nothing short of revolutionary. First, just the speed. A search that could have taken years can now be done in a matter of days. And that speed translates directly into lower costs, because companies aren't wasting a ton of money making and testing compounds that are just dead ends. The computer takes millions of possibilities and boils them down to a short, high-potential list of hits, which just radically accelerates the entire drug discovery pipeline. It's a total game changer. But, and this is a big but, our digital detective is not perfect. not by a long shot. Like any technology, it has its limits. It is an incredible tool for narrowing the search, for sure, but it's not a crystal ball. And it has one major blind spot that we really need to talk about.
And that limitation, the biggest challenge in all of virtual screening, is false positives. This is when the computer flags a compound and says, "This is it. This is a perfect hit, a perfect key." But then when scientists go to test it in a real lab, it does nothing. It doesn't work. It doesn't actually bind to the target. So why? Why does this happen so often?
Well, the problem is that reality is messy. A computer model is a clean, perfect, sterile simulation. But in the real world, the physics of how two molecules actually grab onto each other is just unbelievably complex. Our computer models, as smart as they are, really struggle to perfectly calculate all the tiny, subtle forces at play. Things like tiny changes in heat, the level of molecular chaos, or even the effect of water molecules getting pushed out of the way. Our digital models are brilliant approximations, but they're not the real thing.
And this quote from the source material just sums it up perfectly. Our choices are trapped between efficiency versus accuracy, where even an extensive approach does not warrant higher accuracy. What that means is that scientists are always facing this tough trade-off. They can run a faster, simpler simulation to get an answer quickly, or they can run a much slower, more complex one. But here's the kicker. Even the most complicated, most extensive computer model doesn't guarantee a more accurate result. It's this fundamental battle between speed and true accuracy.
So, let's look at the final report card for our digital detective. The pros? They are huge. This whole process radically speeds things up, it massively cuts the initial costs, and, with the receptor-based method, it can find truly groundbreaking new drugs. But the cons are just as real. It's prone to a high rate of false positives, and its accuracy is always going to be limited by the messy, complicated physics of the real world. And that leaves us with a really fascinating thought to end on. Right now, virtual screening is an incredible first filter, but it's not the final answer, at least not yet. But as our computers get exponentially more powerful and our understanding of physics gets deeper, these digital tools are only going to get better and better. Which leads to the big question. In the future, will the biggest breakthroughs in medicine come not from a test tube, but from a line of code?